Welcome all. Now I am going to discuss question number 11 from the GATE 2020 paper Electrical Engineering. The question is, a single phase full bridge diode rectifier fed from a 230 volt 50 Hz sinusoidal source supplies a series combination of finite resistance R and a very large inductance L, the two most dominant frequency component in the source current R. These are the given options. To know the detailed working principle of the single phase full bridge diode rectifier, audience can go through the given NPTEL course or the video link. Let us have a brief discussion on the single phase full bridge diode rectifier. It is easy to analyze if we consider two cases. Case 1, when the supply voltage is positive. Case 2, when the supply voltage is negative. When the supply voltage is positive, D1 and D2 are forward biased, D3 and D4 are reverse biased. So, the load current direction is Vs, diode D1, load and D2 and again Vs. So, the load voltage follows the source voltage and the load current follows the source current. When the supply voltage is negative, D3 and D4 are forward biased, D1 and D2 are reverse biased. So, the load current direction is Vs, diode D3 and then load and then D4 and again Vs. So, the load voltage is the inverted form of the source voltage and the load current is the inverted form of the source current. But if you observe the left diagram and the right diagram, it is little bit different because the left diagram did not consider any assumptions. In the question, it is given that the source inductance is very large. So, the load current is constant since inductance does not allow the sudden changes in the current. Since load current is constant, the source current is the quasi-square waveform. It will have a lot of harmonics. So, any non-sinusoidal periodic waveform can be represented in its DC and sinusoidal components using the Fourier series, which is given by this expression f of x is equal to a naught by 2 plus summation of harmonics an cos n pi x by l plus bn sin n pi x by l, where a naught, an and bn are defined as follows. Let us solve the problem. Now we need to find out the most dominant frequency component in the source current. So, the Fourier series expressions are given by these equations. Let us find out the DC component in the source current. So, Is, DC component we need to find, which is given by 1 by pi integral 0 to 2 pi Is into d omega t. If we further simplify this expression, 1 by pi integral 0 to pi Is is positive and it is I naught d omega t plus pi to 2 pi Is is I naught but it is negative I naught. So minus I naught into d omega t. If we simplify this expression, I naught is constant. We will take it as common. I naught by pi. Integration of 1 is d omega t only. So, after substituting limits, we will get pi minus 0 minus of 2 pi minus pi, which is given by 0. So, the DC component of the source current is 0. Now, we will find out the AN component of the source current. Source current AN component is given by 2 by pi integral 0 to pi Is is I naught into cos n omega t t omega t. So I naught is constant. We will take it as common. So 2 I naught by pi integration of cos is sin. So sin n omega t by n and the limits are 0 to pi. So n is constant. We will take it out. 2 I naught by n pi. After applying limits, sin pi is 0 minus sin 0 is 0, which is given by 0. So the AN component of the source current is 0. Let us find out the BN component of the source current. IS BN is equal to 2 by pi integral 0 to pi. IS is I naught into sin n omega t d omega t. So I naught is constant. We will take it as out. 2 I naught by pi integral 0 to pi sin n omega t d omega t. If we further simplify this expression, 2 I naught by pi integration of sin is minus cos n omega t by n. The limits are 0 to pi. So 2 I naught by n is constant. We will take it out. Minus is also common. Cos pi is minus 1 minus cos 0 is 1. So 4 I naught by n pi. Yeah. This is the BN component of the source current. So after substituting these expressions in the Fourier source current is 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 equal to summation of odd harmonics 1, 3, 5 to infinity 4 I naught by n pi sin n omega t plus AN component is 0 plus DC component is also 0. So the most dominant frequency components are most dominant frequency components are first and third, implies 50 Hz and 150 Hz. So option D is the correct answer, 50 and 150 Hz. Let us solve the problem in shortcut manner. Shortcut. As we have seen that the source current is quasi square waveform. 0 to pi it is positive, pi to 2 pi it is negative, and it is periodic in nature. It is given by like this, and the magnitude is I naught. 0, this is pi, this is 2 pi. This is source current. See, if you observe this waveform, it is having the equal amount of positive and negative components, which implies the DC component of the waveform is 0. DC component is 0, right? So we need not find AN. So we need not find A naught. Next, if you observe this waveform, it is looking like odd waveform, right? How we can say that it is odd waveform? One can say that how it is odd waveform means I of minus t is equal to minus Is of t. Let us analyze how whether this is odd waveform or not. I of minus t means negative cycle, right? So we will extend in reverse direction. If we extend in reverse direction, it may follow like this. Not it will follow like this. So this is Is of minus t. So now we will consider Is minus Is of t. Means Is of t, we have to invert this waveform. This waveform we need to invert. So minus I of t means positive component will become negative component. Negative component will become positive component. It will follow this pattern. So this is minus Is of t. So if you observe that this waveform and this waveform, these two are exactly looking like same. So we can say this is odd waveform. Odd waveform. So it will have only odd components. It will have only odd components. So the dominant frequency components are first and third. So 50 Hz and 150 Hz are the most dominant frequency components. Most dominant frequency components. Thank you.